Welcome everybody on Zoom. Welcome everybody in the lecture hall. Today we are going to continue what we started on the relational algebra. Remember, it's this beautiful mathematical world where we manipulate and calculate with relational tables, just like we can calculate with numbers. We already looked at a lot of things that we can do. We looked at sigma, which does. What does sigma do? Selection, right? What about pi? Projection. Okay, so I'll give you a few minutes to make sure that you emerge. It's Friday, it's soon the weekend, right? So just a few more hours. All right, so let me ask you a question. These are a few comments in SQL, and I'm asking which one of those is not a DDL comment. Can anybody tell me what DDL means? Yes, go ahead. Maybe the microphone.
Oh, what?
Over there.
Data definition language?
Exactly, data definition language. Thanks a lot. So which one of the following commands is not data definition? Is it create table? Is it alter table? Is it insert into, or is it drop table? There is a majority. Now the next question is the majority correct? And it is, indeed. Data definition is everything that has to do with the schema, the metadata, right? You create your table, you say what the columns are, the attributes, you say what the domains are, you define your constraints and so on. You can drop the tables, you can change the tables, the metadata. But as soon as you start putting data in the table or querying data, this is not DDL, this is the other one. Yes? DML, yes, exactly, which means data manipulation language, exactly, that's DML. All right, so we broke the ice for today. Let's now go back to the slides. All right, so we saw selection, projection, how to rename columns, how to rename tables. We saw also the extended projections. We can create new columns by making computations based on others. All right, well, that's already not bad, right? But then we started looking into something a bit more complex, pushing it to the next level. Now we do things that involve multiple tables, right? Multiple tables, not just one, but two. And this was where I stopped last time. I showed you these two tables and we try to multiply them. So what does it mean to multiply table, right? That's the Cartesian product. Where does it make any sense to talk about the Cartesian table, product of tables? Well, because a relational table is a set of maps, right? So you can do the Cartesian product of sets. So if you do the Cartesian product, you get the union of the attribute sets, the Cartesian product, you get the union of the attribute sets, and then you have all possible combinations. So you have two maps on the left for R, you have three maps on the right for S, so 2 times 3 gives you 6 possible combinations. There's a whole subfield of mathematics called combinatorics that takes these things to the next level, right? So all possible combinations. Okay, we don't need any duplicate eliminations. You can think about it, but basically you don't have to bother about that because if there's no duplicates in R and S, if you just take the combinations, you will also not get any duplicates in T. All right, Now you might have the case, here I did a little change, maybe you notice where this change is. What I changed is that I renamed here E, I renamed it to B. So now we have a problem because we have two columns that are the same. So what does it mean to do the Cartesian products? Well, in that case, there is a clash, there is a collision. So what we do is that we must rename, and we know how to rename, that's row, right? That's the row renaming B to E. So we change B to E in S, and there it solves the problem. Now we can do the Cartesian products. What did we learn here? If you do the Cartesian product, maybe be careful that the supports do not intersect, and otherwise you rename the attributes. Now, another convention that some people have and that you actually see in practice is that if there are collisions, you still do the Cartesian products, but what you do is that you add these little prefixes, right? R.B and S.B, which is a way to disambiguate the two column names, right? And that way you know that R.B came from the left and S.B came from the right. Okay, who is following? Great, okay. So this is the Cartesian product. Now, here is a sign that maybe many of you have not seen before. It resembles the Cartesian product, but we added two little vertical bars in there, right, in order to get this symbol. This is a join. It's a join symbol, a natural join in that case. It means that we take two tables, R and S. Now we have a collision, but that's on purpose. We did it on purpose. We have a column B here that is an integer, and also a column B here that is an integer. And R joined with S, the natural join, is the same as the Cartesian product, plus, you add the constraint that you only combine a map from the left with a map from the right if they have the same value for B, for all the columns that they share. So since the columns that they share here is B, there is no A, no C here, there is no D here, it's only B that they have in common. So you do the Cartesian product, you looked at the matching R.B and S.B, right? So they match here. Here they don't match, 1 and 2. Here they don't match, 1 and 3. 2 and 1 doesn't match. 2 and 2 matches, so I put it in green. And then 2 and 3 doesn't match. And what you do is that you throw away what doesn't match and only keep the two that do. This is a join. So you see that a Cartesian product can be very heavy. I mean, imagine if you have 1,000 rows on the left and 1,000 rows on the right, then you get 1,000,000 rows in the Cartesian product, right? But if you join, you don't have that problem. Typically, you get a table of similar size, and yeah, you basically joined the two tables. When do we want to join? Here I'm anticipating a bit for later. Typically, the two tables that we want to join will be such that we have here a primary key. So B, for example, could be a primary key of S, which is the case here. And B could be a foreign key pointing to B. Do you remember primary keys and foreign keys? This is how we connect tables. So when you have a primary key and a foreign key, what you do, it's very natural, is you join the tables by matching the foreign key with the primary key. And then you see that foo through 1 is a reference here, 1, to this line here. And this is why you put it in, you join it with this tuple here. And here you have bar false 2. 2 is a reference, a foreign key to this row here. So bar 2, so you put, you resolve, so to say, the reference by putting it together here. For whom does that make sense? Okay, so here I'm just connecting the notion of foreign key and private key, primary key and foreign key that we saw earlier. I'm making the connection with the join because this is very tightly related, these two. All right, okay. But now, of course, if you have R.B and S.B and you made sure that they match, why would we keep the two columns? There is no need to keep two columns, it's redundant. So we just keep only one, B, and that's it. This here is the join of R with S, right? It's one of the most complex things you can do in databases, but this is it, we've done it. All right, okay. Now, you have a few things that you need to care about. And again, it's just a bit of common sense, right? For example, what happens if you try to join two tables, but the domains do not match? For example, you see that for R, B is integer domain, and for S, B is Boolean domain. So you will never, ever get a match, right? So what you could do is throw an error, You can also say as a mathematicians, okay, well, if there is never a match ever, then it's empty, right? What I would tell you is to, these are corner cases. It's like the vector space with dimension 0, it's really corner cases. As database people, you really, people don't spend much time thinking about that. The only thing you should remember is that typically when you do a join, you make sure that the domains do match, that you have two columns with the same domains for it to be meaningful. All right. What if you don't have any common attributes? This is another corner case of joining, but again, database people don't care much about that. If you're a mathematician and you still want to, make sure that the corner case is covered, what you can say is that you throw an error, so you don't accept it. You say that if there is no attributes that are on both sides, then you just cannot join. What you can also say is, well, if there is no matching attributes, then we just define the join as the Cartesian product. Why? If it doesn't make sense, then don't worry about that. But for those of you for whom it makes sense, it has to do with the fact that you define the join as the fact that every value with an attribute that is on both sides must match. But if there are no attributes, it's the empty set, the set of attributes. So you're asking that everything in the empty set must match. That's a universal quantifier on the empty set, and it is always true. It's just a convention in math. So mathematicians could argue because of that, there's always a match and you get the Cartesian product. Okay, but really don't worry too much about these two cases. Domains must match and no common attributes. These are really just corner cases. In practice, if you do a natural join, then first, there are attributes that are in common on both sides. And second, the domains will match. This is the typical case. All right, so this is a visual of joining. If you want to, again, have a visual of what's going on when you join, you just match the rows on the left and on the right that share the same value for the column they have in common. In that case, the green column. Okay. Now, there is, let's call it the power user version of the join. If you want to have something more powerful, you could, instead of just automatically relying on the fact that whatever attributes are on both sides must match, you can force your own criterion for matching. You can specify yourself when you consider that a row on the left and on the right match. And in that case, you just add a subscript. So you can see the little difference with before is that here we added this here, A equals D. So you know that you see here the natural join wouldn't make much sense because again, there are no attributes in common, A, B, C, and D, E here. But if you specify that A must be matched with D, then you're just matching this and this, right? So in that case, you build the table, you compute all combinations, but then you must match, this matches, this doesn't, this matches, this doesn't, this matches, this doesn't. So you see, you just identify those where A and D are the same. You throw away everything else and only keep those that match. Who is following? Okay, that's called the theta join, okay? So the theta join is more generic because you as a user has the power of putting whatever you want here in order to specify when something matches and you keep it, or when something doesn't and you don't. If there is no subscript, then it's a natural join and it will just take whatever attributes have the same names. Okay, so now it turns out that now that we have invented plenty of operators in the relational algebra, we can start writing some math. And in particular, we can express this theta join in terms of other operators. In fact, this probably is natural to you, but the theta join is just the Cartesian product followed by a selection, right? So it's a selection based on A equals D of the Cartesian product of R and S. Who understands that formula? For whom does that make sense? Right? It's just a definition of the theta join in terms of the selection operator. So that's the sigma operator that selects on A equals D. And this is applied to the Cartesian product of R and S, that is which would be all possible combinations. Okay, there are a few other equalities. If we consider the intersection, turns out that you can define the intersection of two sets as R minus S, right? So you can try to convince yourself by drawing it or as an exercise. But basically the intersection is whatever is in R that is not, even I have trouble expressing that in plain English, right? But basically you're taking what is in R but not in S, and it turns out that this is exactly what's not in the intersection. So R minus S. Do we have a question on Zoom?
Yes, at theta join, don't we need to get rid of either the A or D column in the end? Or do we keep both columns even if they have the same arguments?
So that's a good question. For the theta join, technically you don't drop it, you keep both, but you can add a pi in on top of it, right? Pi, you can say pi A blah 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 everything except D, right? And then you get rid of D. But this is a step you do manually after the theta join. Did it answer your question? Yeah, awesome. So okay, so there's this. Here's another one. You can define the join. It's a bit more tricky and you need to be a bit explicit, but even the join can be defined as taking the Cartesian product. Then you need to rename, because of course you have two attributes with the same name. So you rename A, assuming A is the attribute in common, you rename it to something else, A2. Then you select on A equals A2, right? That's the join criteria. And then you project on everything but A2. So A, B, and C, assuming this is what there was, and A2, you get rid of it with the projection, right? So you see, with these operators, you can start playing around with the math. But really, when you look at these formulas, you can draw the tables. You can draw concrete examples and draw all intermediate steps, like make a visual of what this looks like, of the Cartesian product, then of the selection, then of the projection. And just in your mind, it's just like you would add and multiply and divide numbers, except that here it's done on tables. Okay. And here I'm throwing at you mini theorems that I'm not going to prove today, but this is left partly to the exercise session. But you know, it's too tempting when you start doing math and defining a relational algebra. For example, you have theorems for numbers that a plus b squared is a squared plus 2ab plus b squared, right? This would be a theorem that you could define. Well, here we have plenty, except that it's for relational tables. For example, selections commute with each other, meaning that you keep selecting. It doesn't matter in which order you do these selections. That's called commutative. So they commute with one another. Selections commute with projections as well, of course, when it makes sense, because if you project away something that you need in the selection, then you have a problem, right? But in general, selections commute with projection. So if you project first and then select, or if you select first and then project, it gives you the same results. Projections commute with one another as well, also whenever that makes sense, right? So you can actually project in a way that commutes. Join, union, intersection are commutative as well, meaning that you can swap them, the two sides, right? A join B is the same as B join A. Join, union, and intersection are associative. That means that A join B join C is the same as A join B join C, right? That gives you exactly the same results. Projection distributes over union. What does it mean to distribute? Distributes, I can do it with multiplication and addition. The distribution basically means that 5 times 3 plus 2 is the same as 5 times 3 plus 5 times 2. You distribute the 5 times over every term in the addition, right? So this is what distribution means. So when we say projection distributes over union, it means that the projection of the union is the union of the projections, right? You basically project the two sides and then take the union. But it doesn't work on intersection subtraction. Selection distributes over union, intersection, and subtraction, interestingly. So if you take the selection of the intersection of two tables, it's the same as the intersection of the selection of the left and the selection of the right. Okay. Join distributes over union as well. And a projection is absorbed by a projection on a smaller subset. So this one is funny. What does it mean, absorbed? So for example, 0 is an absorbing element in multiplication. That means that 0 times anything is 0. right? So 0 is called an absorbing element. So when we say a projection is absorbed, it means that it disappears. So if you project and then project on a smaller subset, then it is it goes away. But again, here I'm throwing plenty of very scary theorems at you that, maybe it's not obvious that it applies and so on, but you'll work about that in the exercises. So let's consider them as homework. All right. Okay, so selection, projection, renaming, Cartesian product, joining, theta join, if you specify the criterion. Who is still with me? Okay, let's look at something else then. Let's look at grouping. Grouping is in fact super important and super useful in data science. It's probably the most powerful of all. It's the sort of things you do. For example, imagine that you have a data set with like it's the Federal Office of Statistics in Switzerland that probably uses plenty of groupings. For example, you have all people in Switzerland with their addresses, and you want to know how many there are in every canton. That's a grouping. It's an aggregation. You count per canton, and for every canton, you are going to give the number of people. This is called grouping, and this exists also in the relational algebra. All right, so what does it look like? So imagine here, I took a formal example, but imagine G is the canton where people live, foo bar and foo bar. And then in A, you might have some, I don't know, people, well, that doesn't make sense, but people per household, let's say. So here we have 19 people here, 20 people somewhere in Canton Bar, 265 somewhere in Canton Bar, and so on, 4 in Canton Foo. So it repeats, right? There's Foo 4, Foo 46, and so on. So what does it do to group? What does it mean? We want to group together all these records that share the same value for G, and we want to aggregate them. So I have a visual for you that I prepared to make it easy to understand. First, that's only in our minds that we do that. This is just a temporary result. First, we rearrange things in order to put together what has the same value in column G. So all I did is shuffling around the records. Here, I just shuffled them around in such a way that all of those that have value foo are here, all of those that have value bar are here, and all of those that have value foo bar are here, right? That's the first thing you do when you do a grouping. Next, you say, okay, that's always value foo. So now I merge, in a spreadsheet, how you merge cells, right? So now I'm merging the 3 cells with the value foo into just one. I'm merging these cells in a single cell, foo bar also in a single cell. Then what do? I squeeze these values into a single value. Let's take the sum, for example. Let's say we take the sum of these 3, the sum of these 4, and the sum of these 2. And there you go. This is the end result. This is the result on the right of grouping the records in the relational table on the left. We group by G, by the same value of G, and on the attribute column A, we aggregate with a sum. For whom does that make sense? What's going on here? All right, perfect. So how can you aggregate? Well, here we use the sum, right? But there's other ways. We can also use the count. Maybe we want to count the number of records in every group. Then it's just a count. We have the sum. We can also sum over them, right? So in that case, that would be 55 for that example. We can also take the average. In every group, we take the average value of A. We can also take the mean. In every group, we take the mean, right? We can also take the max, right, in every group. For example, is what is the age of the oldest person in every one of all of the towns in Switzerland, all of the cities in Switzerland, the Gemeinden? That would be a max. Imagine you have a list of everybody in Switzerland with their age, then you group by Gemeinde, by town, and then take the max in every town. That gives you the oldest person in every town. That's the max. Mode, so of course, then if you're a statistician, you can pick everything that your mind fancies. So the mode, what is the mode? Does anybody know? It's actually the value that occurs the most often. So for example, here you see that 7 occurs twice, but the others occur just once, so the mode is 7, right? It's the value that has the maximum frequency. Okay, you can have the variance. I mean, there are so many of them. You can do percentiles and so on and so on. But basically, if you zoom out, what you need to understand is that these aggregation functions, they have some requirements on the values. For example, if you do the sum or the average or the variance, you need the notion of addition. You need the notion in the case of average of being able to divide by an integer and so on. So if you do the sum, the average or the variance and that and the like, you need a way to add things together, let me say, to simplify. So you need what's called some cardinal semantics. If you compute mean and max, you don't care about summing things. Why would you care? It's just the mean and the max. All you care about is comparing things. All you need to know is whether a value is greater or lower than another value. So if you have an ordinal semantics, meaning you just have comparison, then you can do mean and max. For example, you cannot add two dates, right? So if you do a sum over dates, it doesn't mean anything. But if you take a mean over dates or a max over dates, then that makes sense because dates can be compared, right? October 21st is greater than September 19th, right? For example. So this is why you can take the max and the mean on dates and times. You can also take the max and the mean on strings, actually, because strings can compare, right? You can sort them alphabetically. So that's the mean and the max. And for something like the mode, you don't even need to compare. You don't even need to sum. You just need to test for equality for the mode. You only need to see if two values are the same. So you see that the requirements are different. And what it means here is that which aggregation function you can use when you group things depends on the domain of the attributes that you want to group. If you have numbers, you can use the sum, the max, the mean, and so on. If you have dates, you cannot use the sum, but you can use the mean and the max, and so on. Okay, for whom does that make sense? All right. Okay, now let me scare you with the formula, because every time I showed something to you, we needed a Greek letter, right? So sigma for selection, rho for renaming, pi for projection, and so on. So we need obviously a Greek letter for grouping, and it turns out that this Greek letter is gamma, right? This little symbol right there. This is a gamma. And we take gamma of the table transactions here. So imagine I have countries and cities. I have a price and I have a customer. For example, I don't know, real estate or whatever. What we want to do is group by country and city. Whenever we are in the same city, in the same country, we want to put them in the same group, and we want to aggregate on the other columns, the price and customer. So I already put colors in here to help you. So for example, Switzerland, Zurich is one group. And again, we have Switzerland, Zurich. So these two are in the same group. Then we have Germany, Berlin, again, the same group. And Germany, Frankfurt, that's a third, right? So we have three groups in there. I group on country and city. How do I see that in the formula? Look, gamma, country, city, right? If they are standalones, it means this is what I'm grouping on, right? So now how do I aggregate on price and customer, for example? Well, let's say I want to sum the prices, right? I want to, for example, the total price paid for real estate. So you sum the prices. So I use sum of the price, and then I need to give a name to the column that contains that sum. So let's call it volume. And I use this arrow. Remember, it's the same arrow we used for renaming, right? We sum the price and put that in a new column called volume. Then for the customers, maybe I want to count them. Maybe this is just some customer ID. So it's an identification number for the customers. And I just want to count how many customers there are in every group. So I use the count function, and I put that in a new column called num transactions. All right. So I repeat, I group on country and city, and I aggregate the price into a new column volume, and I aggregate the customer in a new column transactions. What do we get? A table with how many rows? Hint, as many rows as groups. Anybody? How many rows do I get in the output? Three. Oh, that was on Zoom. Perfect. Yes, indeed, you get exactly one row. So here, oh, there's the trick. I need to open the chat and close the chat, and then it's supposed to disappear. No, it didn't disappear. Let's try again. Open the chat, close the chat. Yeah, there you go. So I have three rows. You see, first group, second group, third group. So these are all the unique values of country and city. And here I have the sum. So this is the sum of these two gives you this. The sum of these two gives you this. And the sum of just one number, of course, is the same, right? So this is it. Now I have the counts. I had 2 yellows, 2 greens, and 1 blue. So 2 yellows, 2 greens, and 1 blue. Okay, who understands what's going on here? Okay. So again, I cannot emphasize enough that grouping and aggregating is probably the most important thing you can do when you do statistics and data analytics. This is probably what the Federal Office of Statistics is spending their entire days doing, right? Okay. So this is just a visual, you know, how if you group on the green column, then you basically put together what has the same value, then you aggregate on the other columns. Okay, so this is the grouping. Okay, so now I wanted to come back to something I mentioned earlier quickly, which is the idea that we defined our relational tables as sets of maps, sets. It means that we don't allow duplicate rows. We don't allow a row to appear twice because it's a set. And we also don't care about the order of the rows, right? It doesn't matter what order they are because this is what a set of maps is, right? So this is a relational table. And we have a set of records, a set of maps, a set of tuples, a set of rows, whatever you call them. Okay. But we don't allow duplicates. It turns out that you can tweak a little bit the whole relational model and the whole relational algebra in order to allow for duplicates. All you need to say is you're no longer working on sets of maps, you're working on what is called bags of maps. Bags are the same thing as sets, except that in bags you allow for repetition. You can have several times the same value. How do I see duplicates in there? So let's look for duplicates. We have bar, true, false, bar, true, false. Set of maps that wouldn't be allowed, right? Would be the same map here and the same map there, right? But if we have bags of records, bags of maps, bags of tuples, bags of rows, whatever you call it, you allow for duplicates. And that means that now you might have the same records appearing twice, thrice, 4 times, 5 times, 6 times, and so on. All right. So now we say that the relational table or its extension, if you want to sound fancy, is a bag of records. Okay. So now we'll do this very quickly as an exercise because it's actually amusing to do. Since we defined all of our relational operators on sets of maps, now we need to define them on bags of maps. So we need to redefine the semantics. You will see that it's surprisingly easy and natural to do. For example, let's try to define the union of 2 relational tables, but now these are no longer sets. So it's not the union of sets, it's the union of bags. So if I have, let me test if you get the thing. Imagine I have these 2 tables, R and S, and I have a record, bar 2 false, that is twice in the table on the left and once on the table on the right. More generally, it's m times on the table of the left and n times on the table of the right. How many times do you think I should have this same record in the result of the union, given n, m, and n? It's the union. Anybody on Zoom, maybe?
I see an M.
I think it will somebody else. M plus n. M, we'll come back to M. It actually also makes sense to define something where the result would be M under some circumstances, in that case, because M is greater. But we will come back to it later. But I saw another answer here that was, I think, correct. That was?
There was a 1 as well.
There was a 1. So 1 would be if you add duplicate elimination and come back to a set right after that. So that's also good thinking, right? We could have considered of eliminate duplicates, but I think there was another one, yet another answer.
The ones that see as m plus n 1 and m.
Yeah, m plus n was the one that I was expecting.
And somebody's commenting, depends on the specifics of the union. It can be m or m plus n.
M or n plus n, yeah. So yeah, so I like that thinking. So basically here we are doing the design. Basically we are putting our minds, we are trying to put ourselves in the shoes of the first people who defined the semantics of maps. And probably all the ideas that you have and that you have on Zoom are the ideas that these people probably thought of when they tried to define the semantics. Let's say that the answer that kind of won with the people that defines the union of bags, the one that won is m plus n, in the sense that you just put them together and you just don't eliminate any tuples. So you had 2 on the left, 1 on the right. So 2 plus 1 gives you 3 on the right. Okay, so this is what we do for union. The other answers, just because they didn't win historically, it doesn't mean that they don't make sense, right? You could have considered that people could have made arguments why this also could have been good choices for defining the union, right? So here I'm showing to you the one that won. Okay, so m plus n. Now, the intersection, any ideas of how we could define the intersection of R and S? Again, there will be one answer that won historically, and you could argue that others could have made sense, right? What do you think could be, how many tuples, if you have m times the tuple on the left and n times on the right, how many would it, how many times?
N, the minimum of n and n, sorry,
Yep.
of m and n.
Yes,
Again,
I think
whichever is
exactly,
smaller.
yes, so exactly, both answers are correct in the sense that in that case, n is smaller than m, right? So you're all correct. So in general, it is indeed the minimum of m and n, right? Which in that case turns out to be n. So this is why the answer n is also totally acceptable. Okay, and the subtraction is actually trickier. It's technically the max of 0 and n minus n. So basically, all it means is m minus n, you subtract. But if you get a negative number, I mean, you can try, but I don't think you can imagine a negative number of items in a bag, right? So it has to be positive. So if m is smaller than n, then there is nothing left, and then you get 0. Okay, so you see we can redefine the union, intersection, subtraction. Okay. Then projection, we have a question.
Yes, on slide 77, isn't the first record of the intersection wrong?
The first, let me see. It's absolutely possible. Like everybody, I can make mistakes. Let me see. Foo, 1, true. It appears on the left, it appears on the right. Why would it be wrong? Maybe I can unhide. Yeah. Oh yeah, so it was correct. So so it's important that you understand why, right? So technically we take the mean, so it's once on the left, once on the right, and the mean of 1 and 1 is 1, so we get foo, 1 true. All right, but thank you very much. I mean, again, I encourage critical thinking. I can make mistakes, I make mistakes, and if I do, then you should never hesitate to initiate the conversation and we look at it together. All right, subtraction, projection. So projection, redefining projection is actually straightforward. You just, remove all the columns that are not in the projection, so A and C, but the difference with the set semantics is that here we don't eliminate duplicates. Remember that when we had the set of maps, we had to eliminate duplicates after projecting. So here the only difference is we don't. Okay. What about selection? Well, it turns out that we anyway didn't have duplicate elimination for sets of maps, so it's boring here. Nothing is happening. So for bags of maps, we just do the same thing as for sets of maps here. There is absolutely no difference. We just keep whatever records satisfy the criterion, be smaller than 2 in that case. Okay. Now, what about renaming columns? Also very boring, nothing changes. So if you rename columns for bags of maps, it's the same as for sets of maps, right? Just change the names of the attributes. Renaming a relation, it's also boring, nothing changes. What about the Cartesian products? So for the Cartesian product, all you need to do is when there are duplicates, for example, there is a record that is once on the left and another record that is twice on the right, then you multiply. So if you have R occurrences on the left and S on the right, you have R times S on the right. It's again the historically winning definition because that's the most natural way to combine things, right? For whom is it intuitive that we take the product in that case? Some of you, right, can think about that. Okay. There is a new operation that we add. We didn't have for sets of maps because it was implicit, but we can also add delta, which eliminates duplicates. So you take a bag of maps and you apply delta to, make sure that whenever there is a duplicate, you only keep one. And then you get a bag of maps, but it turns out to also be a set of maps because you kicked out the duplicates, right? Okay, so bottom line here, it was a nice exercise to do with going to bags. The idea is that if you have sets of maps, if you have a relational model and algebra semantics based on sets of maps, you can actually change that to bags of maps or to lists of maps. What does that mean? For sets of maps, you don't care about the order of the records, and you also don't allow duplicates. For bags of maps, you still don't care about the order, but you allow duplicates. So then you can have a number of occurrences of every record that you keep track of. And for lists, not only do you allow duplicates, but the order is important, right? If you change and modify the order of the records, then you get different relational table. Okay. And if you have the list semantics, so if the order actually matters, then you have yet another thing that you can do in a very natural way. It is sorting the relational table, right? That means that you reorganize the records by increasing value. This is also something I'm sure you all did in a spreadsheet, right? To try to sort all of the rows with a specific criteria.
We have a question. Does the order not depend on the chosen domain?
Yes, it does, absolutely. So when you order a relational table, you have to specify on what attributes you want to order. You need to specify ascending, descending, and so on, right?
And another question is, could you name an example when I actually want to have duplicates, hence using bags?
So let me start answering indirectly to the question. It's not exactly the best answer, but what I will say is, in practice, the relational database management systems like PostgreSQL, they do not disallow duplicates. So they actually work on bags of maps by default. So this is more of a real life thing, because I think working on sets would probably be less intuitive to users. Let me think of a good example of that. Imagine you have a database on I don't know households in Switzerland, but anonymized. So all you have is the canton, the town, the Gemeinde, and then the number of people in the households. It means you removed all of the identifying parts, for example, the address, the family name, and so on. In this anonymized relational table, you want a bag of maps. You do not want to eliminate duplicates because you lost the primary key because you anonymized it, but you still want the duplicates because you still have several households that might be the same number of people in the same village and in the same country. Is this example making sense? Yes, awesome. And again, this is real life. So in real life, PostgreSQL is actually going to work on bags of maps in general. And if you choose to, it can also switch to lists of maps. And if you choose to, it can switch to sets of maps if you ask it to eliminate duplicates. But you have to expect that in reality, it's kind of the bags of maps that is the most used. All right. It's the end of that part. And I think it's also almost 11, but is it? I think last time I checked. Yes, exactly, 10:59. So let's take a break. This is the end of the relational algebra parts. And then in the second hour, we are going to look into SQL. You know, this is very theoretical, and I know it can be very complex and overwhelming, and you need to take a look at it offline. You know, the next part is going to be, again, a practical one. So then you can relax your brain again. So I'll see you in 15 minutes right after the break. Thank you.